I'll start from the first demonstration of 3D quantum confinement in semiconductor nanocrystals. Actually, the hidden idea is try to explain how it happened that so unusual, in some sense, material, even 30 years ago, and certainly not well, used in the practice, turns out to be the first material to demonstrate quantum-sized effect. So it was partially some occasion prompted by our mistake, but finally we found that it was, in some sense, it was a lucky choice. So that's why, some reason why I want to speak with this, besides of the Benoit, who insisted that it should be a lot of history. Okay, and after that it will be what about, actually I was going to speak originally, it's about optical and magnetic properties of some metal oxides, and actually it will be titanium oxide and gadolinium oxide. So titanium oxide is a wide gap material with the interband transitions in the deep UV, and gadolinium oxide, even worse, it is vacuum UV. Certainly there is no any confinement effects, or at least we don't know because it is out of the spectral range of our equipment. So we will speak about some classical properties of these materials, like refractive index or magnetism, etc. But nevertheless, these materials may have some applications, and I think it's worth to speak about this. Because not only, we cannot live all the life at the expense of cut selenide quantum dots. It should be something new at some time. And okay, 30 years ago, day one. So particles of cut sulfide, cut selenide, copper chloride and copper bromide were grown in the course of annealing of oxide glass samples loaded with the semiconductor phase. What does it mean loaded? So there are two ways. The first one, as it is in the wet technology, is just put salts. Another one, in some sense, simply because the melting of glass goes on at the 1300 of Celsius. So you can take commercially available powder of semiconductor, cut sulfide, cut selenide, just put the powder, and because of sublimation at that high temperature of the melting of glass, you will have ions of the material, and very soon we found that spectra of optical spectra of these samples, at least some of that samples, demonstrate bulk structure of interband optical transitions. Again, it's 30 years ago, we didn't have any idea. Is it crystalline, amorphous? Is it, platelets, or is it spherical? Because we used X-ray scattering, it just gives some information on average size, nothing more. So we got the confirmations that particles have a crystalline structure of lattice. And soon it was also realized that the growth of the particles in the course of phase decomposition of oversaturated solid solution makes it possible to tune size of the particles very precisely just by changing of temperature of annealing at fixed duration. You can fix for example, the duration and change the temperature of annealing. So 10 hours and this temperature, so you will have different sizes. If you will do it here, you will have different sizes of nuclei. This flat portion, when the particles does not change the size, but when you measure the absorption spectrum, you see that the optical density increases, and decreases. And this part is interesting because there is the size distribution function of nuclei, actually much better than size distribution of the particles grown at the second stage of the process, which is called growth at the expense of soft matter, or the third stage, which is just Ostwald ripening. So the size of the particles been measured with the X-ray scattering. It's cheap and easily available technique. As we see later, it would be better to have a transmission electron microscope, because this case we would not make the mistake which pushed us in the wrong direction for some time. So I will tell you what the story. Just a few words about theory of diffusion-controlled phase decomposition of our saturated solid solution. It was developed by Lifshitz and Slezov in the middle of Second World War, when they've been in evacuation from Moscow in Kharkov. And this work has clearly a military purpose. It was about metallic alloys for tanks. So the work was done in, I think, 1942 or 43, something, but the first publication was in 1954 in GTP letters. So it was military solid theory, and analytical expression being given for any stage. So this is critical radius of nucleation. It is kinetic of the growth at this stage, kinetic of the growth at that stage, at the last stage, size distribution function, analytical. So everything actually was known. And this was very good for us from the technological point of view, because we had some solid foundation to make the process stable and reliable and repeatable. So now we have samples, we have optical spectra. This means that we have energy of electronic transitions, and we have size for each sample. So it looks like we have everything just to claim that we see the 3D confinement of excitations. But our first attempt to fit the experiment to this simple theory, which tells that it should be shift of the energy linearly proportional to the square root of the size of the particles, exactly as it is written in the any handbook of quantum mechanics, with this beautiful picture of rectangular potential with the electron level and the Heisenberg expression below. So that's actually what we expected. It's not surprising, because end of 70s, the quantum well technology was even I think Nobel Prize was given for that time. So it was not a big deal to say, okay, it must be the quantum confinement. Nevertheless, we succeeded to fail completely. And not completely, because for the case of copper chloride, we got the linear dependence, but the effective mass is taken from the slope, as it was written in translation of paper, was odd out of, or many odds out of the literature data. So it was like twice more or less, I don't remember, of what it should be. And for the case of 2,6 materials, even it was not a linear dependence. So we've been, very much confused, and now we, of course, it's obvious now that we just was completely misunderstanding the role of Coulomb interaction in the process of confinement. So now it's obvious, but that time it was not obvious. It's strange, to see how simple things, turns out to be complicated. And that's why we made kind of, wrong move, which is natural. But we thought, okay, there is, effect. We still believed in the quantum confinement, but it is somehow compromised by another possible effect of stress, of pressure, which coming to the nanocrystal when we quench the sample. If there is some mismatch in thermal expansion coefficients, we certainly should have the stress. If, for example, matrix stretch faster than the crystal, it should be some pressure. And it is known that pressure always in semiconductors moves the forbidden gap to the high energies, to the same blue shift. And as we checked in literature, for cut sulfide, for example, it is actually a huge shift. It is 4 milli-electron volt for 1 kilobar. afterwards, with respect to our experiments about phonons, we actually made this experiment with a hydrogenic pressure, and the shift was at the highest pressure about half of the electron volt. So it was a natural mistake, but it was a mistake. And so we, checked the data in literature about thermal expansion coefficient, and we realized that copper chloride is only one, lucky choice for us, because the particles of copper chloride grow as a liquid spherical drops, because the melting point of the copper chloride, even bulk, has like 405 Celsius. And this is below the annealing temperature. So the particles grows at the copper chloride, grows at the spherical drops. So next, when you start the quenching, the drops shrink at crystallization. And at this moment, actually, the size of the nanocrystals should be less than the size of the pore. And more that when we go down further with the temperature, freedom of the particle in the pore increases, because the thermal expansion coefficient of copper chloride is higher than of glass. And I remember it was a joke at that, initial seminars. People say, okay, take the sample and do it like this, like, kids' toy. Is there some noise from the nanocrystals? Okay, so that was motivation to move, because really we thought that, okay, it's only one material which has a chance to show something, because first we have spherical particles, at least we have a hope that the particles are spherical. Second, we know that it should not be pressure, so it should be the clear effect of just confinement. And of course, what was the lucky part of the choice? That's a specific, actually very unusual band structure of the copper chloride, because the spin orbit splitting in this material is negative. And the upper band is just non-degenerate whole band. And maybe there are some other materials, but I don't know. All the materials has, normal, thin blend structure of the valence band. And another feature that the spin orbit splitting of in this material actually very high. And so it gives you again a chance that when you stay nearby of the gamma point, so you will not be too close to that spin-splitted subzones, and you should not worry too much about non-parabolicity of the bands. And third, it was the exciton Bohr radius of in copper chloride is 0.7 nanometer, and we have sizes of nanocrystals more. So what we have from this material, it's spherical particles with no extra pressure, and that 3 exciton associated with the upper valence subband is a quasi-particle with non-degenerate parabolic band. When we go now to the spectra, it's copper chloride spectra of big size, it's 30 nanometers, so that's what I mentioned in the beginning, that some of the samples demonstrate the bulk-like structure and all the peaks of excitonic transition at the right place from the point of view of bulk material. So that is this blue spectrum, which has both peak lines, just where it is written at lower temperature should be. And we see that decrease of the nanocrystal size leads to the blue shift to the higher energy, shift to the higher energy with the decreasing of the size. Okay, so now we should come back, as I said, that we completely misunderstood the Coulomb interaction. And this is 1982, and the first approach to the theory of quantum confinement was developed by Alexander Efros and Alexei Ekimov. Unfortunately, I mentioned that our laboratory moved, and before moving, I've seen the picture 30 years ago, it was Alexei Ekimov, it was Alexander Ekimov, it was me. 30 years ago, I could not, after the moving of lab, I could not find it. And actually, what was important is in this paper, two things. First, it was clearly demonstrated there are two limiting cases of confinement, what's called now weak confinement regime and the strong confinement regime, and the regime depends on the relationship between the size of the nanocrystals and Bohr radius of exciton. And from this point of view, our case of Z3 exciton in a copper chloride just a model object for this theory, which is actually was simple theory because it is for non-degenerated parabolic band. And what we got, this red line, its points are experimental dependence of the spectral position on the reciprocal side. So we see the dream that it is linear, and the slope of this curve gives the value of the effective mass is 1.9 plus minus 0.2, because it's only one parameter to fit. And the bulk value is 2.5 plus minus 0.1. So we think that it's a good agreement, and we really decided, okay, at this moment, yes, this is demonstration of quantum confinement, three-dimensional quantum confinement, okay, an exciton. But still no idea about this line, because it does not fit with the assumption about non-degenerate band. So you see, it's 85, 3 years passed, and the theory of confinement of exciton taking into account that splitted subband, which is non-degenerate, which is degenerated and non-parabolic. And this theory made it possible to describe this line, this dependence, with the parameters of two masses of which we have in the copper chloride. So the mass of exciton, as a translational mass of exciton associated with the light hole and with the heavy hole. And I think, again, the best of our knowledge, this was the first measurement of the value of these masses in copper chloride. So it looks like, yeah, for copper chloride, for that simple situation, the problem is solved, and experiment is happy with the theory. But still, you see, it is 84, and still we have nothing to show and to discuss about 2.6. These are experimental points, and these are just, fit to the beginning, just to give the slope, and nothing more. We know, yeah, okay, this is because there is probability, non-probability of bands, so that's why we have this effect, but not more. And it will have taken many years more, and now we're having 1993, when the theory of how to describe the right samples, I mean the samples which takes, the theory which takes into account the crystalline field splitting and spin-orbit splitting, and this gives a really very nice fit theory with the experimental points for many transitions above of the first transition. So that's actually more or less the end of the story, how the phenomenon of quantum confinement has been confirmed. And of course, between these dates, actually 10 years, it was a lot of other activity. It was a Auger combination and some, it's not like we are sitting waiting for years. We are coming from the past to the future, but not to the future of today, but the future of 2010. So how the future of quantum dots looked, 4 years ago. This is just, that's what's called, it's BCC. There is some company which make, every 5 years, they make forecast for many fields science. And so what you see here, okay, first you see the numbers. So in 2010, it is somewhere here, and the revenue is about 70 millions, actually not a big number for nowadays. And what we see here, it's just one column, which is biomedical, and this is for sure the biological markets, which been commercialized, I think, in 2002 or something like this. But after that, we see appearance of some other columns, and you see the white one appears, which is optoelectronics, and in 2014, again, it's prediction from 2010, it should jump, let me say them, 5-7 times this year. And next year, one more jump. So when I've seen this, data a few years ago, I thought, okay, it's too much optimistic. I don't see any reason to jump. It is written tenfold increase in a couple of years. But now, I think maybe it has some sense because quantum dots go on display. It's just in that, because it is just citation. And let's have a look how they will go into display. It's actually very simple because I will, speak later about actually LEDs, what nanocomposite materials can make for the LEDs, but just a few, words how it works. So what we have now, it's called LED backlit LCD. It works very simple. The blue gallium nitride laser excite the commercial or conventional YAG cerium phosphor, and a portion of the blue light of the LED, which is seen here, by dark blue, then converts into broadband emission of phosphor. So we have some simulation of white light. It's actually bad simulation because what is white light? It is sun, only sun, with the temperature 6,500 kelvins. The next approach is the tungsten lamp with much lower temperature, but nevertheless. And this, okay, there is some special index, rendering index, which actually describe by numbers of the situation. And I think that the sunlight is like 100, and what we have here like 60, 70. But nevertheless, this white light is used as the light to illuminate the backside of the LCD, and that's how we see. And the LCD, subpixels of LCD have the optical filters, which give you red, green, and blue light in the spectral range, which has maximal sensitivity of these elements in eye. I don't know how they call in English, but there are some biological sensitive elements which feel 3 colors. Okay, cool. Mm-hmm. So that's how it works. And what it will be, how actually quantum dots will go to on TV. Very simple, just by substitution of YAG by Katsa selenide quantum dots. In this case, a portion of the blue LED light, this one, is then converted into 2 lights, red and green. And by size, the spectral position of these bands, again, tuned to the filters of the LCD monitor and tuned to the, which in turn tuned to the human eye sensitivity. And this device promises certainly better what's called color saturation, and obviously it will give better efficiency, just because instead of making of the broad spectrum of white light from which only some portions will be used, the system produces the light which exactly fit to the, to the human eye at the end of the day. And that's why it's, it promises about 20% of less consumption of energy. And the problem is that quantum yield of LEDs is actually high quantum yield. Yes, the Munch's calls that it's almost 100%. So I heard about 90%, but again, it's very, very, good quantum yield. But the problem is that this quantum yield is compromised by low light extraction efficiency due to the mismatch of refractive indices of semiconductor and encapsulant. And okay, this shows what happens. So that there is something which called escape cone, and if the p-n junction emits the light with the angle high outside of this cone, so this light starts to travel through the chip, and because normally it's just chip made by broking alongside of the axis, so it's really a perfect perpendicular, and this light will go, forever. It will be lost on the contacts, etc. But at least it should reflect many, many, many times, and this light will be lost. And there are two problems with this. First, it decreases the efficiency of the system. Second, that light actually hit the system because it's absorbed in the chip. And the heating is a big, big problem. You will touch your computer, you will see that it's overheated always. So what can be done? So what's called the high refractive index optical materials. If you will increase the refractive index of encapsulant, it should increase the light extraction from the LED. And how to do it? It's just what's called to me nanocomposite, which actually means that nanocrystals of something with a high refractive index are dispersed in some polymer, silicone, epoxy, whatever. Many things can be used. And depending on the concentration of that nanocrystals of these materials, you can increase the refractive index of the encapsulants, still keep them transparent if you have the small size of the particles, much less than the wavelength of light, and it should work. So titanium oxide is one of these materials because it has really very good refractive index. This is a range of from 400 to almost 800, and this the refractive index changed from 2.55 to almost 2.8. So it's material with a really very high refractive index, and of course it's transparent over the spectral range of visible light. And what we see here, this is just transmission spectra of spin-coated films of this nanocomposite material, which give you the practically flat transmission from 400 to 900 and more. And there is some interference, which is shown in the inside. And this interference makes it possible to calculate refractive index of this film, and this means that material which is used for encapsulant at practically any wavelength which you interested in. LEDs, they have some scattering of power, just statistical scattering. So 10 LED lamps have been taken and measured, and it was a bars here which been fitted with a Gaussian. And the same was done, and this is LEDs filled with a conventional epoxy. And on the right side, it is nanocomposite. So it's the same story, 10 or 12 lamps, the scattering of the power, and this was fitted with the Gaussian. So we can see that both cases, there is increase of the power about 10, 20, 15%, which is quite significant. For both cases of the red LEDs and yellow LED. And the lower picture shows actually stress test, which has shown that in 1,000 hours, the intensity of LED, blue LED, with the encapsulant with this high refractive index material, dropped 15%. So it's a problem of everything. I mean, it's not a problem of quantum mechanics. The problem, if you want to, to have some applications, it's necessary to bridge the gap, the reliability, lifespan of the material. Does not matter, is it encapsulant or it is, some drug or whatever. And here, of course, we see certainly that just for blue LED, for the red, so there is no change. But 15% drop, this means that, okay, you should take it out. And this will be a long activity, how to, I think that's what happened, when Sony decided to make LEDs with that, because there is certainly encapsulant, right? So somehow they solved this problem. Of course, it depends, will it be used in TV or will it be used in, some flat panel monitor, because your, telephone you use, maybe really the monitor works maybe at most 1 hour, right, a day. And the TV works 5 hours. And if we speak about that, solid state lighting, it should work 10 hours. It's all depending on the application, these parameters of, lifetime becomes very important. Just one more example, of possible applications of quantum dots in some devices. So it's implantation technique. Actually, again, long ago it was very, very useful and popular because it has been treated as a way of doping of semiconductors. They thought that it's easy to, to shoot from the implantator the impurities instead of putting them in the growth process. So that's, in some sense, a simple technique. And the energy of the implantation, 450 for cadmium and 330 kiloelectron volt for the selenium, was chosen to fit the parameter, to fit the depth of penetration for both the same, position, the same depth. And again, after annealing, you have some nanocrystals grown in the side of the quartz matrix. So it's actually not glass, it's quartz. So annealing temperature, I think, was more than 1,000 degrees to grow the particles. And the refractive index of this material was measured with a simple prism technique. You can see it here. So initial refractive index of quartz was 1.457. And of course, the effective refractive index of this high, this composite material depends on the concentration of cut sulfide, and it was 1.477 for the 2% weight percent of load, and 1.553 for the 8% of the load. So this kind of active quantum dots, doped, high refractive index materials can be used as electro-optical modulation devices based on the quantum size-Stark effect in semiconductor quantum dots. Why? There are two reasons. First, in contrast to the bulk material, the increase of the gradient of the electric field does not lead to the decrease of the oscillator strength of excitonic transition. The particles are, exciton is confined, so it does not depend much on the strength of the electrical field. And second, technical, because you can make the strip of waveguide quite narrow, so it is easy to apply high voltage, theoretically. Just a few words about vibronic modes. It was a very popular subject some time ago, and the first approach was, a paper of Schmidt, Ring, and Chemla, who wrote that because of the homogeneous distribution of electronic negative charge and positive charge of the hole, in the case of very, very strong confinement, the charge inside of the nanocrystal will be compensated in any point. So the first statement was there is some material without Fröhlich interaction at all. Now, of course, it is, this kind of extreme things, they are not right fully, but in some sense it may be right. So this was the first, and second was so-called phonon bottleneck, which again looks very natural. When you have very small particles, for example, cat selenide, you have splitting of the electronic levels, hundreds of milli-electron volts, and to relax from that level to this level, it should be emission, a simultaneous emission of a few phonons at once, which is not actually very probable. But this problem also was solved, and actually it was solved first again by Sasha, who demonstrated theoretically that the actually relaxation comes not through the electrons and holes, it comes through the electron, and the Coulomb interaction between, it comes through the hole, and Coulomb interaction, electron of hole actually solved the problem. And after that it was shown experimentally by Victor, and I think that second paper was Philippe Chernet about very quick relaxation, thermal relaxation of electronic excitation from upper level to the lower level. And only one question is not actually clear. Yes, okay, we have very good relaxation to the bottom of the to the bottom, to the gamma point, let me say, or to the first level of confinement. And so what? Because we excite permanently, right? This means that we create electron hole pairs which relax and give birth to the phonons. They must go away. And what are the mechanisms? This actually the question is, which I'm going to come. So, but here there is, upper panel is just showing absorption spectra of cat selenide of different sizes, and the bars here are just position of krypton laser lines to excite near resonance, which any actually sample with any size of the nanocrystals. And here there is Stokes and anti-Stokes component of scattering from these samples with a different size of the nanocrystals and different excitation wavelength. So what we see that when the size decreases, the energy of optical modes in the material, in the quantum dots decreases, and opposite for the acoustic low frequency mode, that there is some shift to the high energy and appearance of substructure. So that's, since the Lamb time, it's more than 100 years ago, it's known that behavior of this kind of system, so I mean that vibrational modes, spherical and elliptical vibrational mode of a spherical elastic body embedded in the elastic continuum can be calculated within the rigid and free-standing boundary condition with the use of elastic constants of bulk material. And that's true. So here there is some decomposition of this, low frequency component of the Raman scattering for the modes. And this is dependence of the energy of this frequencies of this mode as the function of reciprocal radius. So it looks very nice, but there is no any sense because these conditions at the beginning say there is no any interaction with the matrix. Rigid state boundary condition, this means that the ions on the surface are fixed. They cannot transfer the movement into the matrix. And the same situation with the freestanding. So if ions goes freely, again, there is no way any energy can be dissipated out of the nanocrystals. Again, theory of low frequency Raman scattering from quartz, whatever, in the relaxed surface boundary condition been developed by Sergei Gupalov and Igor Merkulov. And this theory actually, it's the second publication. So this theory actually takes into account everything. It takes into account energy confined spectrum of the phonons. It takes into account the confinement of electrons, including that problem which was, which took so much time, the real valence band structure. And this curve, it is just calculated spectrum of cut selenide nanocrystals with the radius. No, it's normalized to the radius, so there is just a universal curve. Calculated for cut sulfide, so with the parameters of cut sulfide, transversal and longitudinal velocities, and densities of glass and cut sulfide. You see that the structure is a little bit better resolved than experimental one, but actually it fit, at least qualitatively to what we observe. And the advantage of this approach is that this theory allows partial confinement and partial dissipation of the energy. And of course, this works only if we are sure that there is a contact between semiconductor and glass. And we made some experiment with the hydrostatic pressure, and we saw that the shift starts from the zero. You just start to increase. This means that increase the pressure, and the band gap start to move to high energy immediately. This means that there is no pore, nothing to. It's just in the contact and equilibrium with the matrix. But this is for the case of cut sulfide in the glass in solid matrix. And if we go back to what I was actually spoken about, quantum dot nanocrystals in silicon. I'm not sure 100%, but if somebody will correct me. But I have a feeling that to disperse quantum dots, you need to have surfactant to prevent agglomeration. And if you have surfactant, it means that you have some cloud of molecules between semiconductor and epoxy. I think it's a good subject to think what will be, again, with the energy dissipation. So when Munje will switch on his TV, it would be interesting to know how long it will work. And actually, I think this is, the question which is still formulated, but needs, a lot of effort, not efforts, efforts to answer. And I think that the last topic, and so certainly I'm running out of time. I just, to show that at the beginning, I said that copper chloride is some tricky material. Again, this is the Rabat scattering from the optical modes. And you see that decrease of the nanocrystal size lead to the high energy shift, just because the dispersion, the portion of the optical branch is opposite. So this means that the mass of phonon, optical phonon copper chloride is negative. Not just, to come back, from what we started from. Everybody knows that MRI is actually very popular diagnostic technique, and the most important is, less invasive. So it's more or less good for health, besides of the situation when you use contrast agent. So conventional contrast agent, conventional and commercially available, there are maybe 10 types of them, 5, 8, Bauer, GM, many companies produce and sell them, and they are toxic. And FDA actually issued what they call black label. And this means that doctor will not make the MRI if you don't have some special test about the liver. Because if you have some problem, or someone has problem with the liver, it can be even, death as a result of use of these commercial contrast agents. And that's what, you just, Binat told me about that in Europe people concerned about toxicity. And I think that problem cannot be solved in terms yes or no. And I agree with somebody who said yesterday, if you come with the flu, it's one story. You will not take the cadmium or gadolinium or whatever. But if it is cancer, it depends. So that's why a lot of efforts paid to develop some substitution for that, what's called gadolinium chelates, and one of the candidates, gadolinium nanocrystals, which are supposed to be less toxic, also doped with rare earths with europium or terbium. They can give you different light, red for the europium, green for the terbium, and some. So at some sense they can serve as the markers. And so we developed some technology to grow the nanocrystal for gadolinium oxide with the different sizes. And here there is this how to say that size, mean size, and the size distribution being measured with the dynamic light scattering. And the lower panel show the stability of sample, I think, with the, it's a little bit, it's 95 nanometer size particles, and for, I think, a few months at least, it's absolutely stable, and it's not covered by the surfactant. It's stable at the expense of high zeta potential, which is shown, its stability shown here. This is, it's almost 40 zeta potential, and what actually was the first step and the first goal to see how the relaxivity, and actually relaxivity is a parameter which is used to characterize the efficiency of the contrast agent, and how does it depend on size. And you see there is a actually very quick, very fast decrease of the relaxivity with the increase of size, and it's actually understandable why it happens, because the input to the relaxivity, major input, comes from the molecules which are directly coordinated to the gadolinium ions on the surface of the nanocrystal. So when you increase the nanocrystal size, the surface to volume ratio decreases, and that's why the efficiency goes down. Okay, I think that's time to finish. So thank you very much for your kind attention. Oops. Not like back this way. Okay.